So here we've got a problem where you have a sled that has some forces on it. We're given the mass, and we want to know what the acceleration of the sled is. So we've got forces, mass, and want to know about acceleration. So this is definitely a Newton's second law problem. Looking for the acceleration. So we need to know the net force acting on the sled, and we'll divide by its mass. The mass we've got. And as always, when you are doing out a motion problem, it's generally a good bet to draw a diagram. So here, let's draw a diagram of all the forces that are acting on the sled. So we've got 4.0 newtons to the west. So I'm going to make this way west in my drawing. 4.0 newtons west. 6.0 newtons to the north. So we'll draw kind of a bit bigger arrow going up north. That'll be north. And then 5.0 newtons, 35 degrees north of west. So if this way is north and that way is west, 35 degrees north of west means we start west and then we tilt up 35 degrees towards the north. So this 5 Newton force is going to be something like that, where this angle is 35 degrees, and that's 5 newtons. So north up this way, west out that way, and what we've just done here, this is called a free body diagram, which is all the forces on an object. And one, it's important to note this should only be forces, so there's no like velocities or accelerations on here, and it's just on a single object, or if you're getting fancy, on just one system, but it's just one thing. It's all the forces acting on that one thing, in this case the sled. So the next thing we need to do now that we've got our diagram is decide on a coordinate system. So I'm going to say that up is the y direction and to the right is the x direction, and then I can go ahead and write out my forces. So I can start doing my net force. So the net force is the sum of all of the forces. So let's start with this one, this 6 newtons to the north. So north is my y direction, so that would be 6.0 newtons for y, that would be j hat. And it should be positive because we're headed up, which is the positive y direction. Next we'll do the 4.0 newtons to the west, and so west is headed this way, which is the opposite of my x direction. So that'll be a negative 4.0 newtons I hat, because it's going west rather than, I guess, east, which is our x direction. And then this 5 Newton one. Well, here we've got something that isn't going either in x or y, it's going in both, so we're going to have to do components for this one. So let's go ahead and redraw that triangle. So here is our 5 Newton hypotenuse, and it is going to have an x component and a y component, and the x component will point this way. And we know that angle is 35 degrees. So this side of the triangle, which is adjacent to that angle, that will be the hypotenuse, 5 newtons times the adjacent angle, that'll be the cosine. So 5 newtons times the cosine of 35 degrees. And it'll also be negative, because it is heading in the negative x direction. And then this side here, that'll be opposite the angle, so that's the sine that we want. So it's the hypotenuse, 5 newtons times the sine of 35 degrees. So now we can go ahead and write those in our force up here. We've got, let's see, negative 5.0 newtons times cosine of 35 degrees, that is in the x or the I hat direction, plus 5 newtons, and for the y direction that's the sine of 35 degrees, and that's in the j hat direction. Alright, so we've divvied our vector up into its components, the one that wasn't nicely on our x or our y axis. So we're done with this triangle, so I'm going to go ahead and erase it. So now we've got our net force all in the components. We can go ahead and write it again, add up those components. So in the I direction, we have -4 newtons and -5 times cosine of 35. Let's go ahead and get out our calculator to do that. So this guy is going to end up being -4.0957 newtons in the I hat direction, and this one will end up being 2.868 newtons in the j hat direction. And I'm not going to actually worry about significant figures till I get to the end of the problem. So it looks like we need a little more space here to write our net force in. We'll add up the I components. That'll be this one and that one. So -4 newtons in the I direction and -4 point blah 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 in the I direction. That'll be -8.0957 newtons in the I direction. And in the j direction, we have 6 newtons and 2.86 blah 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 blah. So if we add those two, we'll get 8.868 newtons in the j hat direction. So there's our net force. We've added up all of the forces, all the 3 forces, by putting them in their components and then adding each of the components. And now we can go back here to our acceleration. And this is a vector equation, so remember that means it's actually a couple of equations all written compactly in one. So the fact that we have the acceleration equals the vector net force divided by the mass actually means here, because we have 2 different components to the net force, we actually have 2 different equations here. We have an x equation, which is the x component of the acceleration equals the x component of the net force divided by the mass. Mass, of course, isn't a vector, so it doesn't divvy up. It's the same in both directions. And then we have a y piece of the equation. So that is the y component of acceleration is equal to the y component of the net force divided by the mass. So we can do this in pieces. Gonna need a little more space though. All right, so here I've just rewritten my net force up here, my x version component of Newton's second law and my y component of Newton's second law. So let's find the x component of acceleration. So that'll be the x component of the net force, that's this guy, -8.0957 newtons divided by the mass, that's 22 kilograms. And I don't have to put the I hat here because I've already divvied this up into the components. So remember, the I hat and the j hat, they're just there to remind you this chunk is the x component and that chunk is the y component. But since we were doing an x equation, we know that everything in here is going to be the x component of the vectors. So all right, so here we go. Let's go ahead and calculate that out. That will be -0.0368, and then the units. All right, well, what are newtons? Newtons are kilograms meters per second squared, and we're dividing that by a kilogram. So Newton divided by a kilogram. Here's a Newton split up into its base units, and we have a kilogram and a kilogram. So those guys will cancel, and we're left with meters over second squared. Nice. That's what we'd want for an acceleration. Now let's go ahead and do the y. So the y component, well, we take the y component of the net force, 8.8 blah 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 newtons, divided by the mass, 22 kilograms. Same thing's going to happen with the units here. We'll get meters per second, just what we're hoping for in an acceleration. And then mathematically, that will be equal to 4.03 meters per second squared. So that's our x component, and that's our, sorry, this is our x component here. That'll be our y component. And just like as a quick double check, this component is negative, and it should be negative because we can see the forces intending to pull it off in the negative x direction. This one's positive. Makes sense again. The forces are tending to pull it up in the positive y direction, y is just a little bit bigger than x. Do we expect that? Yeah, because our y force is just a little bit bigger than our x force. So that is what we would expect here. And looking back here, we've got 6 newtons aided by whatever's coming off the component of this guy, and 4 newtons coming off this guy. So yeah, y is probably going to have more acceleration. Alright, so we've solved for the x and the y components. We can go ahead and write acceleration as a vector now. It'll have negative, and let's see, now I guess we probably should pay attention to the significant figures. Up here we have 2 significant figures in all of our numbers. We're doing multiplication to get all of our answers here, so that means we're going to have 2 significant figures in our answer. So the x component is going to be 0.037, because we need 2 sig figs, and therefore we got to round up. Meters per second squared, that'll be the x component. So since we're putting it all together in a vector again, we need the I hat to remind ourselves of direction. And then the y component, that'll be 0.040 meters per second squared. That'll be in j hat because it's the y component. And I suppose we could also find the magnitude and direction here. So let's clear off some space so we can do that. All right, so now we've got some space. So let's go ahead and draw the triangle we need for acceleration. We've already kind of done that for forces, but this is a new triangle. It's for acceleration, not force. All right, so we're going in the negative x direction with our x component. So we'll have vector pointing like that equal to negative 0.37 meters per second squared. The negative, actually, we've taken care of that, I guess, with the arrow, so we can get rid of the negative right there. And then 0.40 in the j direction, and that's up. So that is upwards. 0.40 meters per second squared. And then if we want to make a triangle, go ahead and use our trig functions. I guess that is going to have a magnitude kind of going out like that. So we're just going to grab this chunk, move it over here. All right. So that is 0.40 meters per second squared. Oh, a little messy on the handwriting there. All right, but then we can erase that, and we'll be looking for this angle here and the hypotenuse. So the magnitude of the acceleration is going to be the square root of each of its components squared, each of these 2 sides of the triangle squared. So negative 0.037 meters per second squared, all of it, plus 0.40 meters per second squared, all of that squared. Take the square root of everything. And when we run that through our calculator, we get 0.54, and then units, meters squared over seconds squared, so meters squared over seconds to the 4th. That'll happen in both, which is good, so we can add these 2 terms. But then we take the square root, which undoes this square, so we'll still have meters per second squared, as we ought to. And then for the angle, that was the magnitude. For the angle, we would have, let's see, for this angle, it would be an opposite side and adjacent side, so that's going to be tangent, and since we're finding the angle, it's the undoing of tangent, the arc tan, and you do opposite, 0.40 meters per second squared, over the adjacent, 0.37 meters per second squared, and we have meters per second squared on the top and meters per second squared on the bottom. So those units will just go ahead and cancel out, which is great because the arctangent should never have units on the inside. And so when we run that math, we will find the angle is 47 degrees. And we need to, I guess, say where we're measuring this from. So this is 47 degrees. We're measuring it from west to east, so I guess this is 47 degrees, sorry, from west to north, so 47 degrees north of west. So that's our angle. Should we want to have it in angle and magnitude form, or here it is in components, if we happen to want it in component form. So that is a quick take through of how you use Newton's second law in a problem.